So now we're going to work through a series of progressively more complex situations so that we can give some examples of how to draw free body diagrams. So we're going to start with this simple problem where I have a mountain climber who has mass m who hangs from a rope. And all we would like to do here is draw a force diagram indicating the forces on the climber and find what the tension is in the rope. And so in order to start that, we have to draw some forces. So I know that there is an upwards force that produces a tension in the rope on the climber. And then the climber has some weight. And so we can have the mass of the climber times the acceleration due to gravity. That's the weight of the climber. And so now I have two forces. Let's pick a coordinate system. Here, it doesn't really matter what we pick, but let's say that the upward direction is positive. We don't have any horizontal components to the motion here, so I don't have to worry about that so much. And so we can write down Newton's laws. The sum of the forces is going to be equal to the mass of the climber times the acceleration of the climber. Because the climber is stationary, then the acceleration of the climber is equal to 0. So this equation is always true. It's a special case here that we have 0 acceleration. Now we want to write down the components of the forces that are acting on the climber. And so if I take the upward direction to be positive, I would write that I have a force of magnitude T for tension in the positive j-hat direction. And I have a weight of the climber has magnitude mg that's in the negative j-hat direction. And so I put a minus sign here to indicate that that's the case. So this gives us the components of the forces that are in the y direction, the vertical direction of this problem. OK, so now since I've written down this is a full vector expression, this is a vector, these are vectors, I could reduce this to just looking at the components in the y direction. So I can write the sum of the forces. All I'm going to do is to remove the j-hats and the vector. So the sum of the forces in the y direction are equal to the mass times the acceleration in the y direction, which is 0. And now I would just write T minus mg. Those are the components of the net forces in the y direction. And so it's clear from this equation, since this is equal to 0, that the tension in the rope has to be equal to the weight of the climber. So again, this is a very simple example, but it indicates all of the principles that we just wrote down on the previous slide in terms of figuring out what forces act on the problem, writing Newton's laws. In most cases, we'll skip the step here of writing it out in full vector form and jump right down to components once we've chosen an appropriate coordinate system. Here it was relatively simple because we just had motion, or non-motion, if you will, in the vertical plane. The examples that will follow, things will be a little more complicated. So once we did that, we could write out the component equation, and this leads us to a direct solution for the tension, which is what we were asked to solve for. So now let's look at a slightly more complicated example where the climber isn't hanging vertically. So we have to worry about the different components of the forces when we go to write down Newton's laws and solve here for the tension of the rope and the magnitude of the normal force exerted by the slope. OK, so let's draw in the vectors that we need to solve this problem. So the forces that act on the climber, there are 3. So we have a tension force that pulls the climber upwards. That's what the rope is producing. There's a normal force from the surface that acts on the climber. And then we have the climber's weight, which acts downward. And so through a combination of these, we want to write down Newton's laws and solve for both the normal force that's acting on the climber and the tension in the rope. So without writing any equations down, we can see that just by looking at the vectors, there's some tension force that's holding the climber from sliding down. The only component of force that's pointing down the slope is the component of weight that might point in this direction here. Let's call this mgx. And so in order to solve this problem, we're going to want to break the weight into 2 separate components, one of which is perpendicular to the surface and one of which is parallel to the surface. And in order to do that, we have to figure out the trigonometry at this point. And so if I extend this line down here to the bottom of the slope here, you can see that this is a right angle. And so weight, of course, is vertical. So if I draw that downwards, this is also a right angle. And so what this tells me is that this angle here at the top of the triangle, call this phi, is the same as this angle over here at the bottom corner. That's also phi, which means that this angle up here in the middle is equal to theta, which is the same angle that we have over here, which is the angle of the slope. So if I want to resolve the weight, which is vertical, into components that are perpendicular to the slope and parallel to the slope, I can use theta as the basis of my calculation. So as we move forward then, we're going to actually break the forces into components that are tilted with the slope. So I'm going to draw a y-axis and an x-axis like this, where the y and x-axis are parallel to the slope. And so I'm going to write down Newton's laws in these two new coordinate axes, as opposed to something that's just straight up and down. It's just more convenient to do that for problems like this for the most part. And so we're going to stick with that. So I can write that the sum of the forces in the x-hat direction is going to be equal to the mass of the climber times his or her acceleration in the x prime direction. And so that's going to be equal to 0, of course, because the climber is not sliding down the slope. Now, if I look at these components, the x prime component of the weight is equal to mg, which is the hypotenuse of this triangle, times sine theta. So that gives me this piece here. So I have mg sine theta, and the other horizontal or force along the slope is the tension. Since we chose in this direction down here to be positive from the way I drew this coordinate system, then the tension is actually negative. So this is minus t. And so this whole sum is equal to 0 because there's no acceleration down the slope in this case. So we can write that the tension is equal to the mass of the climber times g times sine theta. So we've solved then for the tension. So that was one of the things that we were supposed to be looking for. So that's a first step. OK, and so now we can exploit the vertical components to find the normal force. So we can write that the sum of the forces in the y, the new y direction, is going to be equal to the mass of the climber times his or her acceleration in the new y direction, because again, there's no motion perpendicular to the slope. This is equal to 0. And so the two forces that are acting in this case, I've got a normal force that acts upward, that's positive, and then I have the component of gravity that acts downward. Before we had mg sine theta, which gave us this component, and so the component that's along the other side of the triangle has to be mg cosine theta. So I need a minus mg cosine theta because that force is pointing in the negative y direction. And so again, since the sum of these forces has to be equal to 0 since there's no acceleration, we can write that the normal force that the slope exerts on the climber is equal to mg cosine theta. And so there we've set out the components of the forces. Here we picked a different coordinate system. It turned out to be convenient to use this coordinate system because most of the forces are either perpendicular to or parallel to the slope. The only one that's not is the weight, which is always up and down. And so we had to break the weight into components. So this was our mgy component, and we had mgx over here. And so once we broke the weight into components, we could write down Newton's laws in components, and then we can solve for the missing pieces, the normal force and the tension of the rope on the climber. So now that we've solved for the tension and the normal force, let's consider what happens to those expressions when we look at various limits of the physical system. So we had written down that the tension was equal to mg times the sine of theta. And we also wrote that the normal force was equal to mg cosine of theta. And so can we, by looking at different limits here, make sense of these that make sure they do something sensible? So let's take and see if we can reduce these to situations that would be common or allow us to check our math. So we already did a problem where the climber was hanging. So if I take the case where theta goes to 90 degrees, say, then in that case, the tension becomes the weight of the climber, which is what we already had. And we can say in this case that the normal force, mg cosine theta, is going to go to 0. So that makes sense because in that situation where the climber is just hanging, there's no surface to press against the climber, and we already solved for the fact that the tension was equal to the weight. So that's a good check for us. Now what happens if we do theta goes to 0 degrees? So that's a different cross-check. And so here, for theta goes to 0 degrees, I would have that the tension goes to 0. Well, that makes sense because the climber isn't hanging anymore. So there's no force necessary to keep the climber from sliding down the slope. And then the normal force goes to the weight of the climber. Cosine theta goes to 1. And so that makes sense too. If I flatten this out, then all the climber is doing is just sitting there on the ground, and so the normal force has to support all of the weight of the climber. So just by looking at these two limits, we can see that this trigonometric expression that we derived actually makes sense when we consider the physics of the situation.